Hi and welcome to this video on numerical methods, and in this particular video we're just going to be looking at how we go about finding a root of an equation when algebraic methods aren't quite going to work for us. So what we've got to do is look at those first three things there. So we're going to look at how we locate the root using a method called change of sign, and then we've got to look at how we get that to a particular degree of accuracy, and then finally we'll talk a little bit about when the method won't work or what particular issues we've got with it. Okay, so here we go, locating a root. So we should know that the root of an equation is the point where it crosses the x-axis. And so if we have a look at what happens on one side of the root, if I pick my value of a, so we can see that f of a is negative, it's coming out with a negative value here. And if we do f of b on the other side, then it will be positive. So what we're essentially doing is just putting in two values, one either side of the root, and saying that, well, if we put in one value, it will be a positive, one value will be a negative, so we've got a change of sign. And exactly the same thing would work if the gradient of our function was negative. So let's have a look at that one. There it is. So again, if we put in values either side and plug them into our function, then we're going to get one positive outcome, one negative outcome. And when that happens, it must have gone through 0 in order for that to happen. And what we can say, therefore, is if we choose our two values, a and b, we can say there's a root in the interval, and what we've got is this square bracket notation here. That's not a coordinate, that's saying it's in between a and b. Okay, now what we're doing here just is identifying where the root is in a particular range of values. What we're not doing at this point in time is finding exactly what the value of that root is. We're just identifying that we know there's a root somewhere within a range, and we can make that range quite small, so we'd have it fairly accurately, but the actual finding the precise location of the root is a technique. Well, there's two techniques, and we'll look at those in other videos. Both those techniques require this change of sign to begin with, so that's why we're focusing on this. And so what we're going to do is prove that the equation y equals e to the power x minus 5 sine x has a root between, we're told we've got to prove the root between 1 and 2. And then we're going to show that the value of that root is actually that correct to 3 decimal places, so kind of two parts to this. So firstly, we've got to understand that if ever we're dealing with trig functions, then we're going to be using radians for our angles. That's a given. So here we go. Let's put some values in. So what I've done is just rephrase that. So I'm saying kind of f of x equals e to the x minus 5 sine x. So doing f of 1, put a value of 1 in, and we get a negative. Put in a value of 2, we get that. And what do you know? We get a positive. So as soon as that happens, this bit is standard stuff. What we're saying is we've got a change of sign, and f of x is continuous, so therefore there's a root in the interval. And that's a statement, that blue statement is one that you absolutely have to include pretty much every single time to get the final mark on this technique. There's that bit in there which says f of x is continuous. We'll just, in the next slide, we'll have a look at why that bit's important. I'm just going to move on slightly for now. Right, next part of the question. We've got to show that the value of our root is 1.609 to correct to 3 decimal places. Now this is where we're given the value of the root, and we can use this change of sign method to identify that that root is correct. And what we're going to do is we're going to have to demonstrate it's in a specific range. So if we think about what's happening, if we're told we've got to prove the root is 1.609, now that's a rounded value. The actual value has actually got to round to 1.609, so that means our value has got to be within those two values there. So we can now use our change of sign method to prove that we've got a root in between 1.6085 and 1.6095. And if we can prove we've got a change of sign or a root happening within that range there as indicated by the red arrow, then we can say any value within this range will round to 1.609, and therefore we've shown that our value of our root is correct to 3 decimal places. So on we go again. Let's just do the same thing now. So there's our first one, in it goes, and we end up with a value in standard form, times 10 to the minus 3. I don't really care how big that number is. All I'm particularly bothered about is the sign of it, and this one here is a negative. And then if we put in our upper value at the upper end of our range, put that in, we end up with a positive value, and therefore we've got a change of sign, so there's a root in this interval here. So therefore, if the root is in, we know the root is now in between 1.6085, 1.6095, so therefore we've done enough to prove that that will, whatever value it will round to 1.609, and so therefore that is our root to 3 decimal places. Right. So that was just indicating this what we call change of sign method. Let's have a little look about some issues regarding change of sign, and the first one is we can get a change of sign if there's an asymptote. If we have a look at the graph above, we've got an asymptote right there. It's a value of x that we can't put into our function because it just doesn't exist for y. But if I take a value below that asymptote, then I'm going to come up with a value for my function that's negative. Put in a value above it, my value is going to be positive. So therefore, we've got a change of sign. So what we're saying essentially is that a change of sign does not necessarily indicate a root. So what we've got is a change of sign, but we haven't got a root in the interval, and that's why our statements to say yes, there's definitely a change of sign has got to include the phrase and f of x is continuous if we're saying there is actually a change of sign indicates a root. So that's why from the previous slide I said we've got to have that statement about it being continuous as well to get a complete definition or a complete statement to say that the root does exist. In this particular case, we can see that the root doesn't exist. We might get a situation where we've got more than one root. So if I pick certain values here, let's pick a value of a that's there, I've got a value of the function that's negative. If I pick a value of b, it's also negative. We've got no change of sign, but we have got two roots. And it might be that we get a curve where those two roots are very, very close together, i.e. in this case, it looks like a quadratic. Could be something else, but let's assume it's a quadratic. It could be that the distance between those roots is very small, 0.1, 0.01, whatever it is, and we pick two values and we completely miss the fact that there's two roots in that range. And that's going to happen when we've got an even number of roots in the range that we're using. And then the alternative to that would be this one, which would pick up, let's say, f of a less than 0, f of b 0. We've got a change of sign in this particular case. So we're okay to say there's a change of sign at interval, but what we're not getting is the fact that we've got multiple roots. And that one's occurring if there are an odd number of roots. Now, in 9 cases out of 10 in the exam, you'll just be asked to say there is a change of sign, and therefore, and if it's continuous, you'll know it's a continuous function, then you're okay. But it might be they start asking you a question to test your understanding of this and whether or not you understand when this technique might fail or give a result that you weren't quite expecting. And it'll be one of these three options. Either the asymptote, or you've got multiple roots where the multiple roots are even, or multiple roots when the multiple roots are odd. Change of sign, but no root. No change of sign, but we've got two roots. Change of sign, but we've got 3 or more roots.